Hi Sudrajat, thanks for your email. I've written out the question that you sent me. You sent me in 3 questions, but I thought I'd just do one of them, if that's okay. This question is here, the first one of the 3 you sent. It's a Bernoulli equation here, and so we make this correspondence to this arrangement here. Bernoulli's equation does appear in my live worksheet on differential equations 1. It's on the 3rd row. There's about 20 integrating factor questions, and then there's about 12 questions on Bernouilli's with a little intro at the beginning. So I'd recommend you have a look at that if you get a chance. So let's have a look at this question. Now right at the outset I can see it's not quite in standard form because this has got 2 lots of, and the standard form for Bernouilli's is in this arrangement here where p and q are functions of x. So if we just divide by 2 all the way through, so I'm going to do that right at the outset and just modify the question that you sent me because that's easy enough to do right at the outset. So I've divided by 2 here, so that cancelled, that's why I got rid of it. And we end up with this, don't we? So now we can make the direct correspondence with the problem, and we'll avoid any confusion, because this is what we're talking about here. So, let the substitution we make then, according to this method, is let z equal y to the 1 minus n. N is 3. So we got y to the minus 2. So now let's get dz dx. Dz dx then. So we need to differentiate this. Minus 2, y to the minus 3, multiplied by, there's something differentiated, so that's dy dx. So that tells us now that dy dx, let's rearrange, is equal to, move the minus over, move the 2 from times down to divide, move the y to the minus 3, which is under here in our mind's eye, up to be with the dz dx. And then write dz dx, isn't it? I've written it from right to left. Let's just check that's true. Leave that where it is, so we left that where it was. We moved the minus over, so here it is here. The 2 went from times on this side to divide on the other. There it is there. And then the y to the minus 3 is 1 over y cubed, so we can move that up to the top on the other side. So that's what we've got for dy dx then. So substitution gives, so let's see what we get then. So dy dx, put this into here, minus a half, y cubed, dz dx, plus, so that's the dy dx, plus y over 2, so that's a half of y, isn't it? Equals a half again, so put that at the front, y cubed x minus 1. Now there's a 2 that we can cancel all the way through, here, here and here on every term, so times by 2 all the way through, gives that. Divide by y cubed all the way through, so let's just leave the dz dx there. If we divide this by y cubed, we'll get 1 over y squared, and we can replace that by z, can't we? So that's z there. Divide this by y cubed, and what do we get? We get 1 lot of bracket x minus 1. So we've done that there. Now what have we done with the signs? We've got a minus here. So there's a minus there. So let's times through by a minus, shall we? So that becomes a plus. This is now a minus, so I'm going to change it on this line here, because it's easy enough to do. And this will be a minus. So I'm going to, that becomes a 1 and that becomes a minus x, so I'll just write that round the other way. So that's a 1 minus x, so just to save a bit of space. Simple little things we've done there. I hope you could see that. Now this is just an equation in integrating factor method, isn't it? In standard form. So here we can circle the minus z is minus 1 lot of z. So I can circle that and write p for the integrating factor method. So here the integrating factor, which we can label as I, is e to the minus 1 dx, integral p dx, which is minus 1 integrates to minus x. So there's our integrating factor. Multiplying then, let's turn our attention to this sub-problem now. So multiplying through by the integrating factor e to the minus x gives, so e to the minus x times dz dx minus e to the minus x times z is equal to 1 minus x and we're timesing that by e to the minus x. So put a bracket around it because it's more than one term. So circle this and circle this. This corresponds to u, this corresponds to b, and we can now write so d by dx of u times v e to the minus x times z is equal to, so there's the left hand side, is equal to this over here, 1 minus x e to the minus x. Integrating now, so we're nearly near the end of the problem now, because it's a simple separating the variables in a sense. Integrating gives, so let's see what we get. The integral of the derivative is just a term inside the bracket, e to the minus x times z. Integral of this side, it's parts. We've got 1 minus x e to the minus x dx. This can be v, can't it? And this can be du in the integration by parts. Standard thing to do. So let's turn our attention to this problem now. So e to the minus x times z is equal to, okay, so it's uv. So u is e to the minus x over minus 1 when you integrate that, times v, 1 minus x, minus the integral of u, e to the minus x over minus 1, changes that to a plus, times the v dx, and when you differentiate these two terms, that goes to 0, this goes to minus 1. So we've got a minus 1 here, times dx. So e to the minus x times z then is equal to a minus, so I can write that round the other way because that'll be an x and that'll be a minus 1. And this will be e to the minus x. And here, when we integrate, we'll get e to the minus x over minus, but there's already a minus there, so that can be a plus. Okay, good. And then we put a plus k at the end here. So what do we get then? So multiplying all the way through now by e to the minus x gives e to the plus x now multiplying through. That will be z. This will be x minus 1. And this will be plus 1 plus k. That's equal to x minus 1 times plus 1 is just x plus k. The only thing what I did forget was this is now e to the minus x. E to the x goes here, doesn't it? And this is an e to the x. Z is 1 over y squared then. So 1 over y squared, so put that in at the end now, is equal to x plus k e to the x. So that tells us then if we invert the two sides, y squared equals 1 over x plus k e to the x. There we go. Now we can square root both sides if we want, get an explicit form, so let's turn our attention to that. So that implies then y is either equal to plus or minus. So square root both sides, you get y plus or minus the square root of this, which is 1 over the square root of x plus k e to the x. There we go. So Sudrajat, that's the answer there then. So I've got a little widget that I also wrote, which is up on Google Play. So perhaps I could flick that one up. I've actually typed in the Bernouilli equation because it's a little solver, little widget tool that I put up on Google Play. Just look up widget integrating factor solution method, and you can type in the problem that we had. So remember we divided by 2 at the outset. So we got a half times I had to put in y is equal to what we had on the right hand side. So here's our equation. So let's just compare this then. So there's the equation. Here's the solution, which is what we got here. So we were on the right track, no problem at all. Plus and minus. So we got that. So how do you solve this equation? Let's just quickly look through these steps here that are mentioned, the step-by-step breakdown here in this little widget tool I've put up on Google Play. So here's the Bernouilli equation, as we said. We write the equation, it's written in like this on this algorithm here. Divide both sides by that value, and there's your substitution for Bernouilli. 1 over y squared, and then you get back to this equation here, which is integrating factor method. Here's your integrating factor, multiply through, and then you can then write down the product, which they've done down here, it's done down here. That's equal to that, and then they integrate both sides like we did, and at long last you get the answer and possible sample solutions there. So hope that's clear, Sudrajat. Don't forget to check out the whole section on Bernouilli's equations if you get a chance. There's plenty of questions there to practice and to become comfortable with this topic. So I hope that helps, and thanks for your email. And if you could, I'd really appreciate it if you like any of the live worksheets I've put up, give us a little rating on Google Play if that's at all possible. Okay, all the best then, Bud, and I'll catch you again. Cheers!